Question 16 says, if the sound level in a room is increased from 20 decibel to 30 decibel, by what factor is the pressure amplitude increased? So, of course, the question here involves sound level, and we know that for sound level, and also we shall use the dependence of intensity on pressure amplitude. So first of all, we know that intensity is proportional to square of pressure amplitude. So suppose the final intensity is I2 and initially it was I1. So first of all, we have I2 by I1 as, let's say the pressure amplitude has increased by a factor of K, then the final pressure amplitude square by initial pressure amplitude square. This is I2 by I1. We have assumed that P0 was the pressure amplitude initially and it has increased by a factor of K, so the final pressure amplitude is Kp0, and that means I2 by I1 is simply K square. This is the first thing that we are getting. And let's look at the expression for sound level. We know that sound level, let's simply call it beta, is 10 in decibel, is 10 log to the base 10 of intensity by reference intensity I0. So if I take beta 2 minus beta 1, beta 2 is the sound level at 30 decibel and beta 1 is the sound level at 20 decibel. So this will be 10 decibel, and let's put it at 10 decibel, and it is also equal to, using this equation and doing the subtraction, we will find that it is equal to 10 log to the base 10. The I0 term will cancel. It is I2 by I1. Okay, final intensity by initial intensity. This in fact tells us that log to the base 10 of I2 by I1 is 1, which means I2 by I1 is simply 10, and this is equal to K square from the equation we had here, and this means that the value of K is simply under root 10. So for question 16, option 1 is the correct option. Let's go to the next question now. Question 17 says the order and velocities of a source of sound S and receivers R1 and R2 are shown. The speed of sound is 5u, then the speed of wavelengths received by R1 and R2 is. Then the ratio of wavelengths received by R1 and R2 is. And this is the arrangement. We have receiver R1 here moving with speed v. We can see that the source is S is moving with speed u by 4, and receiver R2 again is moving with speed u. Receiver R2 is moving away from the source and receiver R1 is moving towards the source. In fact, we know that what is important is the fact that source is moving away from receiver R1 and going towards receiver R2. So that will have the bearing on the wavelength. So to find the wavelength reaching R1, let's call that wavelength lambda 1. So lambda 1 will be the wavelength emitted by the source had the source not been moving. Let's call it lambda naught. And we can see that the wavelength will increase because the source is moving away from the receiver. And what is the amount by which it will increase? It will increase by, in fact, the distance traveled by the source in one time period. So that distance is, well, speed of the source, which is u by 4 into time period, and that time period, let's say, is t. Okay, let's call that time period as t. So we can see that the time period t. So let's now convert lambda naught in terms of time period and u. If I do that, lambda naught is the distance traveled by the wave in one time period, and it is 5u. The speed of wave is 5u into t plus ut by 4. Let's simplify this. This is coming out to be 21 ut by 4. And the wave reaching R2 will have wavelength lambda 2 is equal to lambda naught. In fact, in this case, the wavelength will get shortened by, again, u by 4t. And, well, this will come out to be then equal to 5 ut minus ut by 4. This is 20 minus 1, that means 19 ut by 4. And the ratio lambda 1 by lambda 2, which is what we are supposed to find, we can see that it is equal to 21 by 19, and 21 by 19 is the 21 by 19 is given in option 3, so option 3 is correct. Let's now go to the next question. Question 18 says 3 successive natural frequencies of an organ pipe are 225 Hz, 375 Hz and 525 Hz. If the speed of sound is 330 meter per second, the length of pipe is neglect end correction. So here we have 3 natural frequencies and 3 successive natural frequencies, in fact given as 225 Hz, 375 Hz and 525 Hz. Well, if we look at the highest common factor of these 3 frequencies, we see that the highest common factor in fact is coming out to be 75 Hz, and the 3 successive natural frequencies in fact are 3 times of 75 Hz, and then it is 5 times of 75 Hz, because 5 times into 75 is 375, and the last one happens to be 7 times of 75 Hz. So what this means is that the fundamental frequency is 75 Hz and the 3 successive natural frequencies in fact are the 3rd harmonic, the 5th harmonic and the 7th harmonic. That means the successive natural frequencies happen to be odd harmonics of the fundamental frequency, which actually means that the pipe itself is an closed pipe and the fundamental frequency is 75 Hz. So with that we can now write that 75 Hz, the fundamental frequency, is in fact equal to 1 by 4 times the length of pipe open at one end and closed at the other, into V, and let's plug in the values and to find the value of LO, the length of the pipe. We see that the value of the length is coming out to be V by 4 into 75. The value of V has been given as 330 meter per second, so it is 330 divided by 4 into 75 happens to be 300, and this of course is in meter. So this on simplification is coming out to be 1.1 meter. And if we look at the options, well, option 2 matches with what we have got. So for question 18, option 2 is the correct option. Let's now go to the next question. Question 19 says a 20 watt source of sound of angular frequency 6000 radian per second sends out waves in air. Find the displacement amplitude of the wave at a distance of 1 meter from the source. Speed of sound in air is 340 meter per second and density of air is given as 1.3 kg per cubic meter. So what are the concepts we apply here? Power of source is given. It's like a point source, and the intensity in that case would be, intensity I would be power P divided by 4 pi r square, where r is the distance from the source, from the point source rather. Okay, so this is as far as intensity is concerned, and we can easily find intensity there, but we have to find the displacement amplitude of the wave. So intensity itself we know is pressure amplitude square of pressure amplitude square. Let's call it P square, small p square rather, because capital P is for power and small p here is for the pressure amplitude, divided by 2 times rho into V. This is intensity, and this in fact gives us the value of P square, and P square is then equal to capital P, the power, into rho V divided by, we can see that it is 2 pi r square, and this in fact gives us that the pressure amplitude is under root of P rho V divided by 2 pi r square. And we also know that pressure amplitude P is BK S0, where S0 is the displacement amplitude. So if I substitute here BK S0 for P, we get BK S0. B of course is the bulk modulus of elasticity of the medium, in this case air, and K is 2 pi by lambda, the wave number. So we have BK S0 equal to under root of P rho V divided by 2 pi r square, and so the value of S0 the displacement amplitude is 1 by bk into under root of p rho v divided by 2 pi r square. Now we need to substitute b also, because we also recognize the fact that the speed of the wave, which in fact is given to us, v is under root of b by rho. So it means that b can be written as rho v square, and if we substitute that, then we have S0 is equal to rho v square into k. Again, we have been given angular frequency, so we also use the fact that omega by k is v. So that means k can be replaced by omega by v here. So it's omega by v, and then under root of p power into density into v divided by 2 pi r square. So, well, we have all the values now. It's a matter of just plugging in the values, and if I just put in the values, and in fact further simplify it, because rho and v, they are coming outside the radical sign, inside the radical sign. So we have it as 1 by omega under root of p, and then here it will be 2 pi r square into rho v. So now everything is there. We just have to plug in the values and calculate the value of displacement amplitude. The value of omega is given as 6000 radian per second, power p is 20 watt, r is 1 meter, and rho is 1.3 kg per cubic meter, and the speed of the sound wave is 340 meter per second. If we plug in all the values and do the calculations, we find that the value of S0 comes out to be equal to 14.1 micrometer. So for question 19, option 4 is the correct option. Let's go to the next problem now. Question 20 says, two sources of sound, S1 and S2, are driven by a common oscillator and amplifier. The frequency of the oscillator is gradually increased from 0, and the detector D records a series of maxima and minima. If the speed of sound is 340 meter per second, then the frequency at which the first minimum is observed is... Okay, this is the situation here. The question is based on interference of waves, and we also note that the two sources are driven by a common oscillator. That means they are oscillating in phase, and so we just find the difference of the path lengths S2D minus S1D, and to find S2D we can apply the Pythagoras theorem. So let's find that S2D is coming out to be equal to under root of 80 square plus 18 square, and if you put in all these values, this comes out to be equal to 82 meter, and that means the path length S2D minus S1D would be 2 meter. And for a minima, or rather a minimum to be heard at D, well, this should be, that means this part difference 2 should be equal to 2n minus 1 into lambda by 2, where lambda is the wavelength. But according to the question, we have to find the frequency at which the first minimum is observed, and the frequency is raised slowly. Frequency is raised from 0. So, well, so we are talking about the lowest frequency, and that means the highest wavelength for which this condition has to be satisfied. And if we consider the highest wavelength, we have to take the smallest value of n. In this case, we will take the value of n as 1. So putting n as 1, the equation is 2 is equal to lambda by 2, and this gives us the value of lambda is 4 meter. And if lambda is 4 meter, the frequency f will be speed, which is 340 meter per second, divided by lambda, which is 4. Well, this comes out to be equal to 85 hertz. And well, this is matching with option 2. So option 2 is correct. Let's now go to the next question.